Hello students, my name is Shayan Mitra. I am the faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today I am going to taking the class of electromagnetic wave. The subject code is EC501, and this is the in this lecture I am going to taking the class of electromagnetic wave, and in this section I am going to describe the boundary condition of Maxwell's equation. In the previous lecture, I have described how we extract the Maxwell's equations, the four Maxwell equations in differential form and in integral form using Gauss's law, Ampere circuit law, and Faraday's law of electromagnetic induction. Using those laws and using the and applying the Stokes and divergence theorem, we have derived the integral form, the four integral form of Maxwell equation and four differential form of Maxwell equation. From this in this lecture, we are going to describe how these equations and how the properties of magnetic flux density, electric displacement vector, and the conduction current density, all these parameter how works in a condition in a boundary condition. So let's start with the lecture. Okay, so this is the slide of the boundary conditions. It means that when the field exists in a medium consisting of two different media, the conditions the field must satisfy are called boundary conditions. For the electrostatic field, the following boundary conditions are important. One is dielectric-dielectric interface, another one is a conductor-dielectric interface, another one is conductor-free space. Now in case of dielectric-dielectric interface, suppose in case of conductor-dielectric interface, usually this kind of boundary condition used in waveguide, optical fiber, etc. And in case of conductor free space, we can easily understand that in case of conductor and at the outer part of conductor and the free space in between that, the boundary condition will be activated. So all in these media interfaces, we are going to describe how the display, all the vectors that have all aforementioned, all those vectors will work. So let's go to the next slide. So first one is a dielectric boundary condition. Now suppose now if we take a close look here, that in this slide, that this one is the medium 1. We have taken it as a medium 1. This is the one that I have denoted here, and this is the epsilon 1. Epsilon 1, this is the dielectric constant of the media, and this is the epsilon 2 for the media 2. Now we have already mentioned here that epsilon 1 is nothing but the dielectric constant, and it will be varied according to the media. Now if these two media are different media, it means the epsilon 1 and epsilon 2 is not equal to each other. Epsilon 1 has a different value and epsilon 2 is also have a different value. Now first condition here we have taken here that E1. What is E1? E1 is the electric field intensity. Now E1 is the electric field intensity of this medium, and E2 is the electric field intensity of medium 2. Now as we have know that electric field intensity or electric field is a vector quantity, so according to the triangle law, what we have here, that one vector is ET1, which is describing the tangential component of the E1, and another vector, that is EN1 or E1N, we can notify it with anyhow name. This E1N or EN1 is described as a normal component of vector E1. This is for the medium 1. And now if we consider the medium 2, in case of medium 2, what we have here, that electric field or electric field intensity E2, this also this sign is denoting it as a vector quantity. Now as we are applying the triangle law, what we have here is that E2N is the normal component of E2, and ET2 is the tangential component of vector E2. So in case of E1, we decompose the E1 into vector. One is a tangential component which is named as ET1, another component which is named as en1. Now in case of e2 we have normal vector which is known as, or which is described as e2n or en2, or another vector which is known as et2. So these are the tangential component and normal component of vector e1 and vector e2 sequentially. Okay, now this red line here is denoting the boundary of these two medium. Okay, so suppose now we have taken a area. This is the area that we have taken here, is that a b c d. This is the area that we have taken here. Now what we have here, that these two vector, one is a tangential, one is a normal component. Now this vector, now if we take it as a boundary condition, now this e1 and e2 are the vector of any point of space. It has been described, it has been noted as any point of space in the medium. So suppose we have taken, just for the just to understand the basic physics of how this works, we have taken here as a square value, a square area. Basically we have taken not a square, a rectangular area. Now this rectangular area, what this rectangular area suggesting it, that it is in any point of space. This area can be, this area is describing any point in the boundary space. Okay, so this could be here and this could be here. So if we take that et1 and e1n, what we are having here, that suppose this area, this rectangular area has contain a charge. Suppose this charge is known as rho or rho v, anything. Okay, and here we have already described here, this is the height and this is the width of this specific rectangular area. Now let's go to the next slide, where we are going to describe how this whole picture is going to describe the mathematical representation using the Gauss's law of boundary condition. Okay, so let's go to the next slide. Now here what we have here, we have already described here that the fields are these are the components of E1, these are the components of E2. Now apply the equation E dot dl is 0 to the path ABCDA in the figure. What we have here, that now how E dot dl is 0, we have already know that what we have taken here, that total closed integral of that path, and E dot dl is the infinitesimal small length of that path, and E is the electric field intensity, or it worked as a vector. Now the dot product of the closed path is equal to 0. Now if we apply this equation, what we have here, that ABCDA can be written as E1t del W, E1n del h by 2 minus E2n del h by 2 minus E22 del W plus E2n del h by 2 plus E1n del h by 2 is equal to 0. And from that we can describe here that E1t is del W minus Et2 is del W is equal to 0. From here we can get E1t is equal to Et2. So this is the boundary condition we are talking about, that the tangential components of vector field E are equal at the boundary, and E2 undergoes no change on the boundary and it is continuous across the boundary. So with using this all the components, now if we just go back to the previous slide here, what we have here, that if we take a close look, that this is the E1t. Now E1t is along the del W, so we put the E1t into del W. Look, we have put here E1t into del W, and we have put E1t del W, and we have put Et2 del W. Now where is Et2? Oh, sorry, now Et2 is here. So E1t into del W, this is the first area. Okay, and now this is the direction of, if this is the direction of E1t, now the direction of Et2 along the del W will be minus. That's why we have taken here minus. If we take a close look here, that E1t into del W, and we have taken minus Et2 into del W, because here is the Et2 and here is the Et1, but the direction of the path is different, is opposite for both the cases. When we have taken here E1t into del W positive, then we have to take Et2 into del W minus. So that's why we have put here E1t del W minus Et2 del W. So this condition has been met. Now if you take close look on the normal points, now this one, now we have described here the tangential component of electric field. Now if you take the normal vector, now suppose let's go to the normal vector, how this works. This is the normal vector E1n. Now E1n is basically del h by 2. Now if we take E1n del h by 2, then the E2n del h by 2 will be in minus value. So you look, minus E1n del h by 2 and E2n is del h by 2. Okay, so take a look, E2n del h by 2 and minus E2n del h by 2. Why? Now this is the E2n. Now E2n is in the direction, and along this line we have del h and del h. We have both the value of del h. Okay, so what we have here, we have 1 E2n into del h minus E2n into del h, and the same will be applicable to E1 vector for medium 1. The normal vector will also go along the path, this path, del h and del h. That's we have taken here del h by 2. Now what will happen, this all these four components will cancel it out itself. So we will the residue equation will be this E1t in del w minus E2t del w is equal to 0. So just by cancel out del w we will have this. So from this equation, what we the conclusion is the conclusion that we have made here, that E1 undergoes no change on the boundary, right? It is continuous across the boundary. So the tangential components of electric field vector or electric field intensity will be continuous on the all across the boundary. So let's go to the next slide. Now what we have considered the dielectric boundary condition, where we have taken the electric field. So along the boundary condition, we have concluded that tangential component of electric field intensity will be continuous. That's why E1t is equal to E2t. So let's go to the next, that we have already know that D1t and D2t is the displacement vector. So D1t can be written as epsilon 1 into E1. So now this case also, that what will happen now, as we have concluded that E1t is equal to E2t, now we can written here, we can write that D1t by f psi 1 is equal to D2t by f psi 2. So this is the equation. Now we can write this in this way, that f psi 2 into D1t is equal to f psi 1 into D2t, from that previous mathematical conclusion. Now the tangential component of D undergoes some change across the boundary. As we can understand, the tangential component D undergoes some changes across the boundary. So D is said to be discontinuous across the boundary. The boundary conditions for the not, because as you can see that D1t by D2t is not equal to, is depending upon the dielectric constant of the respective medium. So as we can know that each medium has different dielectric constant. So from the ratio of the D1t by D2t is not equal to 1, it means that D1t and D2t is not equal. We can assume, or we can conclude from this mathematical equation. So from this we have understood that so D is said to be discontinuous. So the boundary condition for the normal components are obtained by applying Gauss's law on a small peel box shaped volume, as in the figure. So we have already know the surface integral of D dot ds is equal to, it means the Gauss's law provided us with the theory or the law is the total charge enclosed, the total net charge enclosed in a surface is equal to the total displacement vector coming out of that surface. So it can be written as surface integral of D dot ds. It means that dot product of the displacement vector and the infinitesimal small surface. If we take a surface integral of the dot product of the displacement vector and the infinitesimal small surface area, we will get the net charge enclosed by the specific surface area. So we can write this is the Gauss's law. This is the mathematical expression of the Gauss's law. Now from that we can describe here that D1n del s minus D2n del s is equal to del q, or it could be written as rho s del s, because we already know that rho s is the surface charge density. And now in the next thing we will going to describe how the surface charge density occurs. Okay, so from this relation we can conclude that D1n is the normal component of displacement vector minus the normal component displacement vector of medium 1 minus the normal component displacement vector of medium 2 is equal to the surface charge density. Okay, so this is the second boundary condition that we have made. Now what is the surface charge density? Now if we have to understand what is the surface charge density, suppose there is a copy, there is an exercise book which has 40 pages. So what we have x, y, z component. We have a length, we have a width, and we have a height of that specific book. Now suppose we start to tear down all the pages. Now by tear down all the pages one by one, now we will reach at a place where we have only one sheet in our hand. So what will happen? What will happen is, it means the length and the width are constant for the specific shape of exercise book, or which could be understandable as a slab. Now what we have done that we just tear out all the pages. It means we have just reduced the height of the specific slab. So just by reducing the height of the specific slab, we have reached to a place where the width is tends to 0, and it can be described as a sheet of paper, just a sheet of paper where we have x and y component. X and y means the length and width intact, but the width or the height is tends to 0. So in that position, if that specific area, surface area, contains a specific charge, suppose that charge is known as q, so the surface charge density of that specific sheet or the specific surface area where the d tends to 0 or the width tends to 0, the surface charge will known as the surface charge density. The surface charge of unit area of the specific space will known as surface charge density, and that could be the physical interpretation of this specific area. So where we have a rho s, this is the surface charge density of this specific area. Where we have the d tends to 0, it means the width is tends to 0. So from that region we have understood that surface charge density of that specific area is rho s. So from that conclusion we can conclude here that d1n minus d2n is rho s. This is the rho s that I have described here, how the rho s has been extracted from a specific space, a specific enclosed area. So from all these equations we have concluded here that dielectric boundary condition have two specific equations, that the dielectric boundary condition will be described by using these two specific equations. One is the tangential component of electric field is continuous along the boundary line. That's why we can describe it using the mathematical interpretation that E1t is equal to E2t. And we have here that d1n is mean, if you take the close look, the d1n is basically a displacement vector that is getting into the this specific surface, and d2n basically this is it will present in this medium, is getting out of the specific space. So what we have from a very easy understanding that d1n minus d2n is equal to surface charge density. That surface charge density is nothing but the surface charge density that has been obtained from the total charge density of this specific area. From this, or it could be realized as a specific page or sheet. From that we have obtained the surface charge density, and this surface charge density from the Gauss's law we can conclude that the displacement vector that is getting into, which is can be described as d1n, minus the amount of displacement vector that is coming out of that specific area, which is known as d2n. The minus d1n minus d2n will provide us the surface charge density of this specific area. So the boundary condition of electric field is E1t is equal to E2t. It means tangential components are continuous in boundary conditions, in boundary, so basically boundary, and the normal vector of displacement displacement vector can be described using this mathematical postulates, is that d1n minus d2n is equal to rho s. So This is the condition, and okay, so and we have this specific figure. Now one that we have described, it could also be described using this specific space that we have. Now we have taken a space, this is as a cylinder. It could help you to understand the basically the electric displacement vector. Now this is the electric displacement vector, that d2, which has a tangential component and a normal component, and same thing will be applicable here. The displacement vector is also has a tangential component and a normal component. So d1n minus d2n will provide you the surface charge density of this specific space, and in this case the del H will tends to 0. Okay, so we have specific surface area in the boundary condition. Okay, so let's go to the next slide. So the boundary condition that we have concluded from all this explanation is that in case of dielectric boundary condition, we have d1n minus d2n is equal to rho s if no free charge exists at the boundary. Now if no free charge will exist in the boundary, what do we have? We have rho s is equal to 0. So from that we can conclude that d1n is equal to d2n. Now if there is no free charge exist in the boundary, we have the normal components are equal for both the medium. And now if Dn undergoes no charge on the boundary and it is continuous across the boundary, what we have, we already know the displacement vector is basically the product of the dielectric constant into the electric field intensity. So from this we can write this, and from this we can write this. So from this equation we can have the the ratio of the normal vectors of medium 1 and medium 2 will be equal to the dielectric constant of medium 2 and dielectric constant of medium 1. So the normal component of D undergoes some change across the boundary. So Dn is said to be discontinuous across the boundary. So what we have concluded here, that from electric field, the tangential component of electric field will be continuous in boundary condition, and in case of displacement vector, Dn is discontinuous across the boundary. So from this all this what we have concluded here, the dielectric boundary condition will provide us with a equation where the tangential components are of electric field are continuous in boundary and the displacement vectors are discontinuous across the boundary. Now this can be with this pictorial depiction we can realize all the mathematical proposition that we have already made here, that d2t, this is the d2 which has a normal vector and a tangential vector. The same will be applicable for here, that it has a normal vector and a tangential vector. The both will be applicable also for E, which has tangential and normal vector. This is the whole picture, and we have decomposed all these factors and we have concluded that two mathematical proposition. Okay, so now here in the dielectric boundary condition we have d1n is equal to d2n. Now we can write this d1 cos theta 1 is equal to d2 cos theta 2. It can be written as also this way. So from this we have, and from e1 to is equal to e2 to we have this, and using 1 divide 1 by 2 we will get this tan theta 1 by tan theta 2 is equal to epsilon 1 and epsilon 2, and this is this specific equation is known as the law of refraction. Tan theta 1 by tan theta 2 is equal to epsilon r1 by epsilon r2. Okay, so this is the law of refraction which we have described here. So let's go to the next slide. So up to this we will conclude our lecture today here, where we have described all the equation. We have concluded up to the law of refraction for dielectric boundary condition, and in case of dielectric boundary condition we have understood that the displacement vector will go through some changes, which is, it means if there is a surface charge density, that the normal vector of the displacement vector, normal component of displacement vector will go through some changes. But in case of electric field intensity, if the tangential component of electric field intensity will not go through any kind of changes, that's why both are going in the boundary. So this through which we have realized the dielectric boundary condition, and we will conclude our lecture here, and in the upcoming lecture we are going to describe how all these conditions that we have already mentioned will act in a dielectric conductor boundary condition. Okay, so bye.